Ladies and gentlemen, good evening, a very warm welcome. So my name is Paul Davies and I'm Director of the Beyond Centre for Fundamental Concepts in Science. As many of you know, this is a sort of cosmic think tank at Arizona State University where we wrestle with big questions of existence, such as the origin of the laws of physics, how life came from non-life, whether or not we're alone in the universe, and why cancer is such a pervasive part of biology. We also take our public outreach program very seriously because it's my personal belief, and I think shared by many of my fellow scientists, that insights from science belong to all mankind, and that the excitement and significance of science should be shared with the wider community. The premier event of our outreach calendar is the Beyond annual lecture, in which we invite a scientist or philosopher of international acclaim to deliver an address in which they think a little bit beyond the strict confines of their subject. No living scientist is more qualified for this role than tonight's speaker, Freeman Dyson. Like me, Freeman comes from Britain, but he spent most of his career at the Institute for Advanced Study in Princeton. He's fundamentally a theoretical physicist, hooray, who helped formulate the subject of quantum electrodynamics, and this is often described as the most successful scientific theory in existence. But that technical description conceals a restless and fertile mind. For Freeman Dyson is a true visionary. He's contributed significantly to a wide range of subjects, from spaceship propulsion and astrophysics to the origin of life and genetics, from the search for aliens to the ultimate fate of the cosmos. And he's probably as well known among science fiction fans as he is among his fellow scientists. His incisive observations about human triumphs and human folly and a scientific age, set out in a series of books, have gained him the reputation as a provocative and occasionally controversial commentator of unparalleled distinction. His inspirational thinking led to the award of the 2000 Templeton Prize. And just today, incidentally, it was announced that the 2012 Templeton Prize will be awarded to the Dalai Lama. And now, just to some organizational matters, could you please turn off your cell phones? I did with mine already. And let me tell you a little bit how the evening will work. Freeman will talk for about 45 minutes. Then I'm going to call upon my colleague, Lawrence Krauss, to moderate the questions. And we've tested the acoustics here. We don't need microphones for the questions, so you can just shout them out, and we'll repeat them if necessary. And then, when the evening terminates, Freeman has very kindly agreed to sign copies of his books, which will be for sale in the foyer outside. So I think we can all look forward to a very enjoyable evening. And ladies and gentlemen, now please join me in welcoming the 2012 Beyond Annual Lecturer, Freeman Dyson.
So I can't see your faces, but anyway, we'll have to make do. Thank you, anybody who was involved in inviting me here. I don't know who you are, but anyway, thank you very much. It's a great pleasure to come, and sorry I won't have a chance to get to know many of you, but anyway, I'll be around for 3 days at the workshop, which is going on this weekend. So some of you, I hope I'll see there. The talk this evening is really just a sort of historical reminiscences. I'm a historical monument. I'm one of the sort of survivors of the lucky times just after World War II. I was just tremendous luck to be around at that time, beginning a scientific career, having survived the war. We all felt just we could do anything. The worst had all happened already, and we didn't need to be scared, and so the world was up to us to manage. And at the same time, it just happened by some remarkable historical chance that 4 technical revolutions were happening right away, just in those first 2 years after World War II, the four revolutions, which I'm going to talk about today, being nuclear energy, space, computing, and the genome. All of them essentially started in 1945. And this is not so much about science, it's about technology. It changed the whole conditions of life for a large fraction of the human species, and will continue to do so. And that's, of course, why this was an exciting time to be young, and it's even an exciting time to be old. Anyway, so let me start. There was space. And I was introduced to the space age. I lived in London at that time. And Werner von Braun had developed the first spacecraft, the V2 rocket, which was an amazing technical achievement. The V2 essentially had all the essential features of liquid fuel rocketry, very well worked out. And it actually flew, and it came down on London. And we enjoyed listening to these rockets come down. It was wonderful for the morale, because these were supersonic all the way down to the ground. So it meant you heard bang first, and then you heard the whistle of the rocket coming down. You knew it had missed. So it was actually a very cheerful experience. And what was much more so, it was even much more cheerful, because we knew at that time that this was actually the unilateral disarmament of Hitler's Germany, that Hitler desperately needed airplanes. The German Air Force was just fighting a heroic battle to try to protect Germany and protect the German troops with an inadequate number of airplanes. They desperately needed fighter airplanes, especially. Every single V2 rocket was just about equivalent to a fighter airplane in technology and in cost. So by throwing the rockets at London, he was actually destroying a complete air force for no military benefit whatever. And the strange thing is that Hitler actually knew that von Braun afterwards published his memoirs, and we know what happened, that he had a conversation with Hitler when the V2 program began, and Hitler understood very well what it was all about. Hitler asked the right question. He said, "Can you make millions of these?" So Hitler said, "All this is nothing, this is just artillery, that's all it is. Just another way of lobbing explosives over onto the enemy." And we all know artillery only works if you have very large volume of fire. You should think millions rather than thousands. And von Braun said, "Jawohl, mein Führer," and then Hitler never followed through. And so von Braun actually promised him to build millions. There was never any question of building millions. He couldn't have, even if he'd wanted to. Von Braun simply took advantage of the situation to promote his own agenda, which was getting to Mars. So we were always very grateful to von Braun. He helped us win the war. And we afterwards, of course, welcomed him here in America. At the same time, Arthur Clarke was just starting his career. Arthur Clarke was a young engineer working for the Royal Air Force, and he invented satellite communications. He wrote a paper for the magazine Wireless World, which was published in 1946, I think it is, describing satellite communications. Essentially, he had the whole thing, what you could do with satellites, which was clearly the start of the space industry. He got it right. And at the same time, he also published a short story, which was the very first story he ever published, called Rescue Party. I don't know whether any of you read it. I read it, and it's a wonderful piece of writing, because Arthur Clarke, besides being technically very imaginative and technically exact, he also is a great writer. And anyway, this story, Rescue Party, a marvelous story about a galactic civilization which hears too late that there's a new intelligent society which they're getting radio signals from in a remote planet somewhere out on the edge of the galaxy. And that remote planet unexpectedly became technological very fast. And then they learned that the sun around which this new society is orbiting is about to become a nova and is about to explode. And so they sent a rescue party in the hopes that they might just rescue a few of the inhabitants of this planet before it's destroyed in the nova explosion. And they arrive there only a few hours before the explosion, and they find the planet deserted. And anyway, you have to read the story. It's a wonderful story, and it describes a possible future for our planet. That, of course, it was our planet that he's writing about. And anyhow, after that, there was a long pause in the space business. I was extremely impatient. I thought things would go much faster than they did. We were waiting and waiting and waiting year after year. We thought after von Braun had given us a good start, we would all be flying spaceships in a few years. Instead of that, nothing happened. Until about, 8 years later, Sputnik went up, and suddenly things started to move. And so Sputnik shook the world, and that was a wonderful time. Of course, I was by that time an American, and I got invited to join a nuclear rocket project in San Diego called Orion, which never flew, but it was great fun while it lasted. That was a nuclear space project, putting together the advantages of nuclear bombs with the advantages of big spacecraft that could zoom around the solar system. And we seriously intended to go. We were not just joking. We were going to go to Mars, and the place, one of our favorite places to go actually was Enceladus, which is one of the moons of Saturn, which we chose simply because all that was known about it was it had a very low density, which meant it must be made essentially of water or snow, ice, and therefore would be a good place to refuel our ship and get drinking water for ourselves. So Enceladus was number one to visit. And now we know, after 50 years later, that it actually is one of the most exciting places in the solar system. And there's something weird going on, which we don't understand. There's some hot gas jets coming out of the south pole of Enceladus. Nobody understands why or how, but it's something very unusual going on. And so it's, of course, one of the possible places to look for life. So if we had gone there, we would have actually found this, and would have been even more exciting than we imagined. Anyhow, history passed that by, and that's where I was put into a difficult situation, since I believed in nuclear energy, and I also believed in disarmament. And the two, of course, went together. If you had a nuclear-powered spacecraft, it would not only zoom around the solar system, which was good for science, it would also get rid of bombs, which was good for disarmament. So you'd kill two birds with one stone. And we hoped, in fact, to have an agreement with the Russians. I did talk informally with Russians about this. They agreed it was a good idea. And so we could have gone ahead with the Russians, actually, with a bilateral disarmament program, throwing bombs into space. It's the most satisfactory way of getting rid of them that I could imagine. However, it had one fatal flaw, that it also poisoned the Earth and made our planet radioactive. And that was a problem we could never really solve. And that was the primary reason why it didn't fly. We were perfectly well aware of that. It was something we tried very hard to deal with, but essentially you couldn't. There was no way you could fly Orion without contaminating the landscape in a fairly drastic way. So after the Nuclear Test Ban Treaty was signed in 1963, Orion was certainly dead. And I worked on it for a year and a half, and that was the time when we still hoped actually to fly. But in the end, of course, it was just a study program. Nobody took it very seriously. And meanwhile, von Braun went ahead with his Apollo program. Both of them were, in a way, good programs, but both of them had the same flaw in a way that they were not sustainable. That was particularly true of the Apollo program, that it was announced by Kennedy in 1961, I guess, that we get to the moon and back within the decade, and that was it. So it was a 10-year program, announced as a 10-year program. And so you spend all the money you have with this very limited goal, and then after that it's done. And there was never any thought of continuing for 100 years, which is what is needed if you really want to go ahead. So it was in a way misconceived from the beginning. I'd like to sort of to give grades to these revolutions. There were 4 revolutions, and I would say, roughly speaking, there was 1 complete failure, there were 2 half successes, and 1 complete success, 1 really spectacular success. And it's fairly obvious which those are. The complete failure is nuclear, as we envisioned. I mean, we all thought, not just me, but even the most respectable people in particular, I mean, great scientists like Niels Bohr and people who consider themselves statesmen, really believed in nuclear energy as a salvation for mankind in some sense. So it's something really big that would transform the economy of the planet, make the poor rich, make the deserts bloom, all this lovely rhetoric. That the energy would be freely available to everybody. That would be the great equalizer. It would mean there would no longer be rich countries and poor countries. We'd all be reasonably well off. Nuclear energy would flow and solve all our terrible problems. Of course, that didn't happen. And there are many reasons why it didn't happen. One of them, of course, is the problem of nuclear contamination, which has always been a worry. The problems of nuclear accidents, which I'll talk about, and much more fundamentally, the fact it never became cheap. Nuclear energy always remained sort of marginal in cost. If you did the accounting creatively, you could pretend that it was cheap, but it never really was cheap. And that was really the fundamental reason why it didn't ever supplant other kinds of energy, except locally. I mean, in France, it has done well. In various other countries, it does reasonably well. But on the average, it hasn't made a big difference. If you look at the other revolution in which I was mostly concerned, the nuclear one, I mean, no, the space revolution, this has been, of course, a huge triumph for science. Space science has been an enormous success, and it still is so. Everybody probably here has heard about the Kepler mission, the mission for observing transits of planets going in front of stars by doing very, very precise photometry of stars. It's a very simple mission, just a little spacecraft with a little telescope staring at a whole lot of stars and observing very precisely changes in the brightness of the stars when the planets go back and forth in front of them. And this is just such a simple idea It works spectacularly well. The reason why it works so well was the technology of information processing has raced ahead during these 50 years, so that now we can process information and transmit it over these huge distances amazingly cheap and amazingly fast. You have this broadband communication, gigabyte bandwidth over interplanetary distances, and it's small and it's cheap and it works, it's reliable, all the things that we'd never really dreamed of at the beginning. So the space science has been spectacularly good, and it's getting cheaper and cheaper and more powerful as we speak. So halfway, the space revolution has been a huge triumph. But in the meantime, of course, there's been the whole manned program, which has really gone nowhere. It's been a terrible disappointment to those of us who really believed in it, that the manned program, it has to be done on a 100-year timescale. There's no other way. You want people, not just people, but life as a whole, spreading out in the universe. That's not something you can do in 10 years. It has to be incremental. It has to be slow and steady. And actually, you have to think in centuries rather than in decades. And I had a happy experience just 2 years ago. I visited Baikonur, which is the Russian space center, which is actually now in Kazakhstan, but the Russians wisely hang on to it, just like the British used to in Hong Kong, that the British had a 99-year lease in Hong Kong, so it still legally belonged to China, but Britain was allowed to run it for 99 years. And the same is true now for Baikonur. Baikonur belongs to Kazakhstan, but the Russians are running it. And it's still the center of the Russian space culture, you might say. It started out like JPL as an army rocket program, and the great rocket designers were all there, and the Gagarin, the first astronaut who first went into orbit around the Earth, lived there. And it's the place where the Russian space culture is seen at its most intense. And it's still used as the main launch center. And they still use the old Soyuz launch system, which essentially is the same thing, the same rocket that launched Sputnik now 55 years ago. And wonderful old reliable rocket. Low-tech, it works, it's beautiful. And anyway, I had the pleasure of being there because my daughter is a cosmonaut, and my daughter, in fact, got trained in the Russian space system and was ready to fly as backup to Charles Simonyi, who did get to fly. Is this thing working? It's okay. Now, anyway, tell me if you don't hear me. Anyway, Charles Simonyi was also got trained at the same time as a cosmonaut, and so he was able to fly, and just in the hopes that he might fall down the stairs or succumb to Spanish flu or something. My daughter went along as the backup, but anyway, fortunately or unfortunately, Charles went up. And anyway, we all got to, the whole family went along, both families, and enjoyed the launch. And what was really striking about this is that the vision we had of the Russian space culture, which is so different from ours, that they think in centuries, we think in decades, and it makes a big difference. So in the Russian system, the launch is a civic ceremony in which the whole town takes part. Everybody comes out on the streets, and it was a horrible day with wind and rain, and people came out with umbrellas, but they were all there. And so then the astronauts or the cosmonauts in this case, parade through the town, and they are received in the town square by the municipal authorities, and they have formal speeches, and the cosmonauts salute and say, "We're ready to fly," and then it's all done very ceremoniously, and there is, in fact, an Orthodox priest in there and various other dignitaries. And so it is something you do. It is as they said, I mean, we're on our way to the stars. It doesn't matter how long it takes. We're on our way. That's the feeling the Russians have. It was they who invented it, after all. Tsiolkovsky was the first real imaginative writer about space. He understood what you had to do to get into space. He worked out the equations. He wrote stories, and he started the whole thing in the 19th century. And, of course, they started the Sputnik, and they also built the space station, essentially. The space station is really there. It's just an enlarged version of Mir, the Russian space station. And in Baikonur, you can see there's a huge museum in which there is a full-scale model of Mir, and there's a full-scale model of the big space station, and you can see they're essentially the same. They're very proud of that. Of course, in the United States, we just don't think that way. We're thinking, what do you do in the next decade? What's the NASA budget going to be? What projects are actually going to fly right now? And what's the mission? And it's a different way of doing things. The American way is very good for science. The Russian way is much better if you're thinking of a long-term culture that's really going to last. Anyway, so that's my view of space. Let's talk a bit about the other things that were going on. In 1944, Oswald Avery, who was a professor at the Rockefeller University in New York, discovered the function of DNA. DNA, of course, had been known for a long time as a chemical that was in big supply in cells. It was known that it was a big component in the nucleus of every cell, but nobody had any idea of its function. And it wasn't supposed to be concerned with genetics because it was much too simple. Genetics obviously had to be very complicated. We knew that genes existed, and the genes somehow made an egg into a human being, but they must be very complicated to do that. Whereas DNA was ridiculously simple, just seemed to be a long sort of linear string molecule, couldn't possibly do something as difficult as that. Well, what Avery discovered experimentally was that DNA actually was the gene, and the way he proved that was he transferred DNA from one bacterium into another. It was done with the pneumococcus bacterium, which causes pneumonia, and it was a well-known bacterium, and it had several different strains, some of them virulent, some are not virulent. And he showed that just by transferring the DNA from a non-virulent bacterium into a virulent bacterium, you could make it non-virulent, and vice versa. So it was clear the DNA had to be the gene in order to do that. So that was the revolution, that we knew that genes actually were simple. And from there on, it was just a question, how does it do the job? Finding out the details. And it was obvious that was going to be something very big. And it happened, actually, I had a rather inglorious part in this revolution. I happened to know Francis Crick, who was, I think, 6 years older than I was. So he was very old. He was 26, and I was 20, and I worked for the Air Force, and he worked for the Navy. This was during World War II. And, of course, he was terribly depressed and miserable because the war hit him at the worst time. He was 21 when the war began. which was just the worst time. And so he'd lost 6 years of his life doing naval intelligence, which of course, it's they say military intelligence has the same relation to intelligence that military music has to music. And anyway, Crick was just thoroughly sad and depressed. He knew that he was never going to amount to anything as a scientist, as he had already forgotten almost everything he had learned. And he had been trained as a physicist. So he had the question then whether he should actually go back to doing physics or whether he should make a completely new start in biology. And I gave him some very good advice. I said, well, you know, biology is going to be the most exciting thing, but it will be too late for you. It is... It'll take 20 years before biology can really take off and become really exciting. And by that time, you'll be too old. And of course, anyway, fortunately, he did not take my advice. And so 7 years later, he proved me wrong by finding the double helix. And anyway, so that's history. But of course, the genome revolution has also been only partly successful up till now. We had expected two things would happen. First of all, it would be an enormous thing for science, that we would discover what life is actually all about and understand biology in some deep way. And that really has happened. That's 100% successful. But we also thought we could solve problems of medicine, cure cancer, cure rheumatoid arthritis, all the other terrible diseases. And of course, none of that has happened. It just takes a little bit longer. And it's an interesting question, why it's so hard. I think it's sort of becoming obvious in time that the digital world isn't enough. And that's, of course, a subject which is, it happens, my son George has just written a book called Turing's Cathedral. So now, I'm sorry, it's a commercial interruption. Anyway, my son is a historian, and he writes about the history of technology. And he describes this development of computing, which is the fourth revolution, which I shall talk about, essentially as a cathedral built on a foundation, which is a paper written by Alan Turing in 1936. And the paper is called On Computable Numbers. And I remember reading that paper myself in 1942, which was before anybody thought about electronic computers. And I read that paper, which came out in a mathematical journal, and I remember thinking, oh, this is wonderful, this is beautiful, this is something great. It was just understanding in principle what you could compute and proving a deep theorem about the existence of a universal computer, that is in the digital world, that you could make a computer that could do everything that any other computer could do, could simulate any other computer, and it still there were questions which it could not answer. So Turing had all that. It was a marvelous piece of work, but I never imagined it could lead to anything practical. And I don't think Turing did either. I think, in fact, I mean, that only came later. It was purely theoretical. Well, the interesting thing is, this is something that very few people are aware of, that 30 years, no, more than 30 years, it's about 50 years later than Turing, there were two mathematicians in Minnesota called Poor and Richards, who published a paper about analog computing. And they're just pure mathematicians. This is just pure mathematics, nothing else. They prove, but it's a real solid mathematical theorem. They prove there are numbers that can be computed analog, but cannot be computed digital. So in principle, analog computing is more powerful than digital computing. I think that's a very fundamental truth, which we have not yet come close to exploiting. Of course, everybody imagines that analog computing is just a thing of the past. You know, there used to be things called slide rules that people used to use for computing, and that's an analog computer. That's the kind of thing you think of when you think of analog. It's very old-fashioned stuff, low-tech. And meanwhile, of course, the digital world has gone racing ahead. Everything modern is digital. Everything old-fashioned is analog. But that's not going to be the way it is in the end. And I think, in fact, we can already see the beginning of a new analog world. When you look at things like Facebook and Google, I mean, that things which, and actually in our own brains, I believe the same is true. Associative memory. We have this amazing ability to associate pictures in our heads. We have no idea how it's done. You see one person's face and you think immediately of another. And somehow or other, the pictures just flow into each other. And how is that done? Is it analog or is it digital? And most people imagine nowadays, since digital is fashionable, people imagine the brain is digital, that somehow the brain computes all this by somehow farming it out to neurons, and neurons behaving like little counters with zeros and ones. And I don't think that's true. I think the neurons probably are more analog, but we don't know. There's absolute total ignorance there. But anyway, it's worth thinking about. So I have the feeling that the analog revolution is still to come, and it'll be just as exciting as the digital revolution has been. So let me talk a little bit. I'm getting sort of disorganized, but it doesn't matter. The computing revolution, of course, started in World War II. There were in 3 different places. There was, first of all, the British Bletchley, the place where they decoded the Enigma, deciphered the German communications during the war. That was immensely important for the war, and Turing himself was there. Turing took a big part in that. And so that was, you might say, the first really powerful use of electronic computing. There was a thing called the Colossus, which was actually built at Bletchley, which I would say was the first really operational electronic computer, but it didn't have software. It was sort of a hardwired computer, which was very fast, but not at all flexible. It was designed for a specific purpose. And there was a similar thing at the Aberdeen Proving Ground in Maryland, working for the United States Army, computing artillery trajectories. And then there was von Neumann's computer in Princeton, which was the first non-secret electronic computer with software. The essential invention of von Neumann was software, not the computer. The idea that you could actually treat numbers and instructions together and compute them both. So the instructions for the computing actually got computed along with the rest of the program and modified the operation as you went along. So that was what that was what made computing flexible. And the Princeton computer then was a big part of my life. It was a great fun. I was there when it started, and it was running for about 5 years, and it was a huge success. And we did essentially 3 things with that computer. You had 3 groups of people, and there were the spooks who came at night and did hydrogen bomb calculations. That was, of course, a very important part of it, but we weren't supposed to know it was happening, and it was quite obvious. And then there was the climate part, which was out in the open, and that was wonderful. That was the best collection of meteorologists in the world. We had really good people. Jules Charney was, I think, the sort of the moving spirit, a great meteorologist, and lots of other people, Rossby and Fjortoft, and the people who are well known in the climate business, Smagorinsky. Anyway, so they did the first climate models, the first weather prediction models, and of course it was very, very hard going. They had a tiny memory. The entire memory of this machine was 5 kilobytes. It's unbelievable how much you could do with that. It's very, very clever using the memory over and over again. And they did, in fact, compute the weather and did 24-hour forecasts almost as fast as the real time. But it started the whole industry, and we started already in those days thinking about climate. And Jules Charney, I remember, was very much interested in that. It was obvious that climate was going to be one of the big applications. And the third application was biological evolution. And that was really a one-man show, a Norwegian called Baricelli. I think he had an Italian father and a Norwegian mother, but he was actually himself a Norwegian, but with the name of Baricelli. And anyway, he came to Princeton to use the computer to do evolution on the machine. And he did amazing stuff. It was 50 years ahead of his time. He actually evolved artificial life. He had populations of little creatures, very simple, but with the essentials of life. They reproduced, they mutated, and they ate each other and parasitized each other. They could form multicellular systems. And they could evolve. That was the important thing. And he actually saw evolution happening. So this was, in fact, the first demonstration of artificial life. And it was amazing how much he could do. And that got totally forgotten. His papers were published, but nobody paid much attention. And it all had to be rediscovered 30 or 40 years later. Anyhow, we missed a huge opportunity. After von Neumann died, the Institute for Advanced Study, in its wisdom, scrapped the whole project, decided they didn't want to have these dirty-fingered engineers soiling their teacups. And there's a famous memorandum which actually exists in the archives, a memorandum from the director of the Institute to John von Neumann, complaining that his engineers are drinking their tea with too much sugar. So that was the kind of culture clash that was involved. So they were very happy to get rid of the engineers and get rid of the machine. And we lost the whole thing. It was a shame. I mean, two new sciences were just about to be born. One was climate studies. The other was computer science. So the actual development of computers as an academic subject. Both of those we had in our hands, and we threw them away. It's a great shame. I think it would have made a huge difference. As you might know, I happen to be a sort of a dissident on the subject of climate. I think climate science has been very badly politicized in the last 30 years. And it's a very unfortunate situation that climate science has become a political football and subject to huge political pressures. And I think we could have avoided that if we had gone ahead with climate science in the 1940s before it became political. Chances are it would be very different from the way it is now. Oh, that's the end of the political part of the talk. And it's interesting to look at the history of computing as it has actually happened, because it's so totally different from what we had imagined. That's always true with new technologies, that in many ways they fall short of what you expect, and in other ways they vastly exceed it. And so that's what's happened with these computers. When von Neumann was designing his computer, I mean, I talked with him in those days, and he never imagined that the thing could become small and cheap. He thought of computers as being part of the establishment, that those were big, big machines run by experts, owned by big organizations, either by the government or by big companies or by the military. And so he asked us, on some official occasion, he was asked how many computers would the United States actually need, and he answered 18. So that was the idea. I mean, one for each department of the government, roughly. And instead, of course, it went in completely the opposite direction. That instead of getting bigger and bigger, it got smaller and smaller. And the way it has gone, it has become so much more creative than we ever imagined. That you had these little devices that now are toys for 3-year-olds, and everybody has them. And of course, the world has changed very drastically as a result. And I would say, on the whole, the change has been good. It has essentially empowered the individual as compared with the big organizations. And to my mind, that's good. It has its downside, of course, too. But anyway, I would say the computer revolution really has paid off to an amazing degree. But, of course, it's a problem for science. That we reached a point. There's a book about this called by Jim Glick, which you might have seen, called The Information. So it's a wonderful book. I strongly recommend it, which is about the history of information. Glick is a good writer, and it's a non-technical book. It starts out with African drums, which is a beautiful subject. It turns out that the fastest communication channel 200 years ago or 300 years ago was in fact African drums. They could transmit information faster than Europeans using ponies. I mean, the fastest communication in Europe was essentially ponies riding with messages. That's the way you got information fast from one place to another. Essentially the speed of a horse. But the drums could go faster than that, because they had a drum language that they could actually represent the syllables of the language by 2 notes of a drum, upper and lower note. So you needed only 2 drums, and you could transmit speech. And that's what they did. So when the Europeans got to Africa, they were amazed that the natives in a village knew they were coming, even though they'd never been there before. And the Europeans never figured it out. And in fact, I think the first European who actually became fluent in the drum language was an Englishman who was a missionary who actually wrote a book about it. And that was not so long ago, I think in the 1930s, he wrote this book. And then, of course, one of the sad consequences of the computer revolution is cell phones. Now every African village has cell phones, so they don't play the drums anymore. And well, the problem is that information has got so cheap that it costs much less to collect information than it does to understand it. And the turnover happened the year 2000, roughly. So the big turnover when information became cheaper than understanding. And that has actually hit all kinds of aspects of culture. It's a problem for historians and linguists and artists as well as scientists. We're drowning in a flood of information. And it's wonderful, but it's also very difficult. So I'd look at my own subject, which is, say, astronomy. Well, it's not really my field, but it's a field I'm familiar with. Astronomy is in a golden age. We have wonderful things going along. But you don't need to look at the sky anymore. It's all there on the database. And so I was listening just the day before yesterday, I was listening to a talk about runaway stars, which is a beautiful subject. We're learning a lot about the way our universe is put together. There are stars which are found running away from us at very high speed, so fast they'll never come back. So they're going out of the galaxy 800 kilometers per second, that kind of speed, so fast they'll never come back. And what does that tell you? Well, how do you get a star moving that fast? It's not so easy. But there's one way you can do it, we know for sure. And that's if they happen to be a binary star, a double star, with two big stars revolving around each other, which happens to go very close to the big black hole at the center of our galaxy and gets disrupted. So the two stars get detached from each other. And it can happen then with some quite large probability that one of the pair goes into the black hole and gets swallowed, and the other gets thrown out. And that's the runaway. So the runaway borrowed the energy from the black hole, and the other star made up for it by getting swallowed. So you can actually learn a lot about the black hole by looking at these runaway stars. And that's a very beautiful part of astronomy, which is just now beginning. This is all new. It's just all happened in the last year or so. And how can you discover these runaway stars? It's almost impossible to tell if you look in the sky, because they're so far away. They're very faint, and they don't look different from other stars. So there are billions of stars out there. And how can you possibly tell? Well, the way you do it is we have already in digital memory a thing called the Sloan Sky Survey, which was done over the last 12 years, which put the whole sky into memory. So that's where the information flood comes in. We have this enormous flood of information. The entire sky with billions of stars and hundreds of millions of galaxies it's all there, and it's measured in 5 colors with high precision. And so you can actually then pick out, if you have the data processing power, which we now have, you can actually process the entire sky in a few days and pick out stars with exactly the right characteristics with the 5 colors. So you know they're intrinsically very bright, but they look faint, therefore they have to be very far away. And then you look, you with a much bigger telescope, you look at these candidate stars, measure how fast they're actually going away. And you can find whether they really are runaways or not. And anyway, so that's the way astronomy is now, that you don't need the sky anymore, all you need is the database. And the same thing, of course, is happening everywhere you look. And that, of course, is connected very much with the genome. If you look at the way genetics is done nowadays, it's very similar. And it is good for young people like you, though I can't tell how young you are, but I have to watch the clock. It's pretty much we're coming to the end of the time. So the genomes are being sequenced with about the same acceleration as computer power, which is a thing called Moore's law. Moore was a designer of integrated circuits and who started out the computer industry in the modern, doing integrated circuits on silicon. And he formulated Moore's law, which said the volume of computer power and goes up by a factor of 100 every decade, and the price goes down by 100 every decade, which is roughly the way it's been for 5 decades since he promoted that law. So that's why computers now are cheap and powerful and simple and small. The price has gone down by something like 10 factors of 10 in 50 years. That's the price per bit of information. And the volume has gone up by 10 factors of 10 in 50 years. Well, the sequencing is doing the same right now. That a number of base pairs sequenced, that's units of DNA, follows essentially the same law. So that means we're up to, at the moment, about the human genome was done 10 years ago, which was of the order of a billion bytes of information, what we call a gigabyte. We're now up in the range of 100 gigabytes of genetic information, something like 100 equivalent human genomes. But it's rising at the rate of a factor of 100 every decade. So 2 more decades, we'll have done the whole job. We'll have sequenced the entire planet, everything that lives, at least one genome per species. We know there are about 20 million species, and we know roughly how many genes they have and how many base pairs. So something like 2 decades more, we'll have done the entire biosphere. We'll have a catalog of everything that's alive. So we have a chance then to understand ecology in some sense. We'll have the same sort of grasp of ecology as we now have for individual creatures, which of course means not much. We have the information, but we don't have the understanding. And that's going to be the future of science, that there will be more and more this enormous flood of information coming in. And in the case of the genome, it's remarkable how small the total is, that when you compare it with other things, I mean, if you take the DNA for the whole planet, that's one set of genes for every species, it's altogether about 1 microgram of DNA, tiny, tiny amount. And it's only about 1 petabyte of data, which is small compared with Google or compared with any of the big databases we're using. It's about the same as the Digital Sky Survey, which is old-fashioned, 10 years old. So there's a huge amount of information in living creatures which somehow is not in the genome. And I had a vivid demonstration of that. I happen to have identical twin grandsons, George and Donald. And so we were doing a cloning experiment. Anyway, so George and Donald have exactly the same genes. We've actually also got from 23andMe, the company that does human genomes, we actually got genomes for Donald and George, and they are really identical. And so that's actually a test of the technology, that they are actually identical to 1 part in 10,000. And anyhow, so they have exactly the same genes. But when George was 6, he came up to me one day and said, Grandpa, why am I George and not Donald? And I couldn't answer. After all, I have the same genes. Why am I not the same? And that's so that's what we don't understand. That to make a human being is a very different thing from just having a set of genes. So the humans are unique in a very different way. So something is there in the human personality which is not in the genes at all. And that's something good for the future. And I have a strong suspicion that it has something to do with the fact that analog is more powerful than digital. The genes are digital. That's the beauty of DNA. It is digital. That's why we can handle it so well. It can be computed with our existing technology. But what makes a human being, of course, is much, much more. And I have a strong suspicion it's going to be analog, but we'll see. Anyway, so the next revolution, I should talk just for 5 minutes about the future. As they say, it's always easier to predict the past. But anyhow, there is a future. And I'm very excited about something called HAR1 and HAR2, which some of you may know about, and that's neurology. Neurology, I would say, is sort of the next unexplored territory. That's the human brain and brains of other creatures with which we share the planet, and this wonderful thing which we are aware of, our own consciousness, which we don't understand at all. And anyway, there's something called HAR1, which was discovered about 5 years ago by a friend of mine called, what's he called? Horseman, but I forget his first name, it doesn't matter. He's a professor at University of California, Santa Cruz. And he's actually not a biologist. He never got his fingers messed up. He's a computer scientist. That just shows that because of this information flood, it's easy to hop around. That's what I was going to say when I got sidetracked before. That if you're young, it's easy to switch from one field to another. Because every field is more or less using the same tools, namely big databases. And if you can understand one, you can understand another. So you can switch easily from computer science to biology. That's what Horstman did. And so what he did was to take the already computed genomes, which are all there, for the chicken, the mouse, the rat, the dog, the chimpanzee, and the human. I think he did 6. And you take those 6 genomes and you look at them carefully, and you pick out the pieces which are exactly the same all the way from chicken to chimp, but very different from chimp to human. And those are the pieces he was interested in. There are 2 of them, actually. So there's HAR1, which stands for Human Accelerated Region 1, and there's Human Accelerated Region 2. And both of them are doing something very important, but we don't know what it is. But you know they have to be important because they were not changed all the way from chickens to chimpanzees, which meant something like 300 million years since the separation between birds and mammals, which was sometime in the reptilian age, 300 million years ago, so they had a common ancestor. So since that time, those pieces of DNA have been doing something so important that it could never be changed. But between the chimpanzee and the human, it changed dramatically. Something like 18 different changes happened, and that was only 6 million years from the common ancestor of the chimp and the human to the present. So something happened to change the function of that piece DNA. After changing its function, it changed its sequence as well. Same was true for HAR2. So then you see what more do we know? There are 2 things we know about this, which both of them indicate the way the thing is going. That first of all, when are these particular pieces of DNA active? We know, first of all, they are not genes. They don't code for proteins. So they're doing something different. They're doing something to organize whatever it is, not directly producing anything. They're active. You know exactly when they're active because you can look at the RNA that they're producing. And they're active in the 2nd trimester of pregnancy. That's in the embryo, which is exactly the time when your main body plan is being laid down. The structure of your legs and arms and toes and fingers and everything else is being established during the 2nd trimester. That's from 4 to 6 months, or whatever it may be. In the case of the mouse, it's not quite the same. But anyway, so we know when they're active. It's during the crucial phase of the development of the embryo, which is what you would expect. So then the other question is where they are active, and then you can easily guess. Anybody like to guess? What? Yes, the cortex of the brain. That's HAR1. What about HAR2? What? What? No. What? What did you say? Louder? Hand, yes. Wrist. It's the wrist particularly. Anyway, so those are the 2 things that make us human, the cortex of the brain and the wrist. So anyway, I find that very exciting. It's again a beginning of 2 new sciences. First of all, the question, what does that 97% of the genome actually do, the part that's not coding for genes, not coding for protons? So the genome is 3% genes, 97% we don't know. So that's unknown territory. And the other question, of course, is why are we different from chimpanzees? And that's, I think, one of the most interesting and exciting questions we could possibly be thinking about. So that's my sort of prognostication for the next revolution, that It'll have a lot to do with neurology. And so I wish you well. And
Thank you, Freeman. I'm Lawrence Krauss. I'm privileged to be Paul's colleague, both in the Beyond Center and also directing the Origins Project. And we're very privileged by the fact that Freeman will be here for the weekend, and many of you, if you want to see him again in a slightly different context, can come to Gamage Auditorium on Saturday night for the great debate on the origins of xenophobia, where Freeman will surprise and upset people. And in fact, that's, I never have listened to Freeman and not been surprised, sometimes upset. I was very lucky to spend a year at the Institute for Advanced Study, where I took every opportunity to spend as much time with Freeman as possible, especially every lunch hour. And every time I came down and I talked to him, and this is a warning for you who are about to ask questions. I would ask a question, or I'd say, you know, I've got something and you're finally going to agree with me on this. And he never did. So I think that's appropriate now to begin to ask questions. I don't know if we can turn up the house lights at all so we can see who's asking questions. Oh, I'm beginning to see people. Okay, excellent. So I think I'll choose questioners, and Freeman could choose to answer them.
good.
And we'll go on for about 15 minutes. So we'll take it over there in the back. Yes, you. Yeah. Mm-hmm.
You said you were disappointed with the outcome of the nuclear science revolution, but isn't that primarily for political reasons that, for environmental reasons, so on, the nuclear energy was squashed, whereas in France, for example, as you pointed out, it's done quite well. So is it more a political problem than scientific one?
Well, of course, it's both. I mean, it is, of course, true that it's done well in France, but it hasn't really transformed the society there either. I mean, France has chosen to use nuclear power on a large scale. That's fine, it works, but it's not drastically cheaper than other kinds of power. It doesn't make all that much difference to daily life in France. It provides employment for a lot of highly skilled technical people. That's good, but socially speaking, it hasn't been the kind of revolution we had in mind. So anyway, I could give a whole hour's talk about nuclear accidents, which is a very interesting subject. I mean, roughly speaking, I would say that the nuclear industry...
Can you hear him? Okay, I think your mic isn't working. Let me just check this out. Being the theorist that I am. Okay, let's try here.
Does that work?
Yeah.
That's better. Good. Anyhow, it happens that there was a genius in the United States Navy called Admiral Rickover, who started developing nuclear power for submarines and did a marvelous job. And it had very unfortunate effects. That he designed reactors for submarines which worked. The Navy has done extremely well with them because the Navy knows how to run machinery. They have people who do things right. They follow the orders. They don't goof off. And so, as a result, the Navy reactors actually work very well. Unfortunately, they got ahead of the rest of the industry. But when civilian nuclear power began around the 1950s, Rickover's designs were already there, and the simplest thing to do was just copy Rickover, and that's what the industry did. So all the existing reactors, except the ones in Canada, and a few others around the world. But in general, more than 90% of all the power reactors, including the ones in France, follow Rickover's design. They are light water reactors, and the essential feature they have is high power density. And the reason they have high power density is if you want to put a reactor into a submarine, it has to be high density. Submarines have very little space. And so that's why they have high power density. And so if you copy the design, that's what you get. And what you need for safety, of course, is just the opposite. If you had started with the idea of safety as an overriding consideration, which they should have, they would have gone immediately for low power density. And that is, in fact, not very difficult to do. You just have to have a different kind of design with lots of concrete and some cheap material which absorbs heat, which you can make very large and massive. And you can make the thing so big that it will absorb the heat for 2 or 3 weeks after you shut it down. And that's what we should have done. And so you could have made a really completely safe nuclear power reactors if you had not followed Rickover's designs. But the way the industry works, it's always cheaper to copy somebody else's design, and then the regulations then get written so as makes it very difficult ever to change. The regulations, in fact, are written more or less to say, yes, do it Rickover's way. That's safe by definition, and anything else you want to try is not according to regulations, therefore not safe. So the whole thing becomes stuck. So anyway, that's, to my mind, the reason why it's extremely hard now to shift to a different style of nuclear power.
Okay, good. We have time for a few more questions at this rate. I wonder if I'll take any from up. There's someone, yeah, you, and then I'll come back down here. Yes, you're the one. He's up there.
So first of all, the question was, what do I think about cancer research? I happen to have a lot of good friends who work on cancer research, and I don't know anything about it myself. I'm quite ignorant, but it's clear that they are struggling very hard to disentangle the genomic basis of cancer, and that's, to my mind, is a very good way to go. I mean, it seems to me it's a problem of just masses of information, but the information is there. The problem is trying to understand it, to find out what really is the sequence of events that causes the cells to go bad. But they're learning every month, they're learning new things. And once in a while, you do have a medical success. They had a success recently with melanoma, which was quite remarkable. And so from once in a while, something very good does happen. It's usually with a small fraction of cancers of a particular type. The fact is, it's a very complicated disease. There are very many different varieties. It's going to be a hard slog. But I think we are getting there, and I'm very hopeful that if you look, say, 50 years ahead, we probably will have really good treatment for cancer, and that's, of course, what we all hope. Yes?
Oh, okay, you chose someone yourself. Oh, this little fella? Yeah, okay.
That's a very good question. Why hasn't the analog computing revolution happened? And the answer is, of course, these things always take a long time. And so you never know when it's going to happen. All we know is there's a mathematical theorem that analog computing, in some mathematical sense, is more powerful. And somehow, sooner or later, we'll make use of that. But nobody knows how. And I think to some extent, it may well be that Facebook is using it in a way. I mean, that there is this whole universe of software programs based on pictures is somehow leading toward the replacement of digital by analog, but I don't understand the details at all. But I think that it probably will come somehow that way, that there are so many of the practical applications that are interesting for human reasons where analog is the natural language. That's particularly true of pictures, of course. And so it probably will happen, but I have no idea when. You probably will live long enough.
Now we'll take this gentleman.
Okay, what's your opinion of the Leonard, Tanner, Fonda, Weissman, William Larson, that idea that we can have fusion reactions at low temperature?
The question is, what about the idea of having fusion reactions at low temperature? Yeah.
Low energy nuclear reactions?
Well, let me just say two things. I mean, you can buy for $200 a toy called the Fusor, which is built in Canada, and it's everybody can have one for their kids. It's a very nice toy. It actually does fusion. It's a real, honest-to-God fusion device. It produces neutrons by fusing deuterium. It's based because the reason why it's made in Canada is the Canadians have lots of heavy water. So it has heavy water as the working material. And it does actually fuse deuterons to make neutrons quite substantially. I mean, it makes something of the order of 1 million neutrons per second. You can have one on your dining room table anytime you want. And so there's nothing wrong with that. It's all a question just how much. And what Pons and Fleischmann thought they could do it on the scale of watts, it turns out to be wrong. I mean, that it is a good evidence that that didn't actually happen. The Fusor is producing a fraction of a microwatt. And of course, for a useful fusion device, you'd like to have megawatts. So there are 3 different orders of magnitude. Microwatts you really can do, watts you probably cannot do, and megawatts you'd love to do.
Sounds like life in general.
Yes.
Okay.
Well, I don't have anything much to say about that. It's not my field. I actually used to be a particle physicist, and then when it became too difficult, about 40 years ago, I quit. Yes.
Okay, you have the last question, so it better be good. Okay. Yeah, there you go. The squeaky wheel. Okay.
Good.
One question.
Well, actually, I'm very, very skeptical, having brought up 6 kids of my own. Everyone is different, and so I'm skeptical about.
Creativity, engineers and the artists to work together instead of separating them. How can we bring them together for the sake of creativity?
Well, anyway, I hear what you say. I don't happen to believe it, but that's, I mean, there's nothing personal about that.
I think disagreeing is perhaps the best way to end this, and I will call upon my colleague Paul Davies. Thank you.
Well, thank you, Lawrence. Thank you, Freeman. It would be quite wrong for us to leave this wonderful evening without my paying tribute and saying thank you to my many helpers. These events don't just happen. There's a huge amount of work that goes into them. And I'm especially grateful to Carol Hughes, who handles our media and communications. She's here somewhere. To my student helper, Catherine Lee, but most especially to my assistant, Adriana Fontes. So a round of applause for them. I hope they can hear it. And as previously indicated, Freeman has agreed to sign copies of his books. They're in the foyer outside. We have a secret passage we're going to take, so we will see you there in a few moments. And for those who are not going to stay, be sure you drive safely. Thank you. Good night.